before we solve some differential equations, which have discontinuous functions on the right-hand sides, I would like to talk a little bit about the Laplace transform and jump discontinuities. So let's first look at a very familiar function, f of t, which is 0 when t is less than a, and is 1 when t is bigger than or equal to a. And this is our definition of ua of t. We've Laplace transformed this before. It's e to the minus as over s. Now let's look at a very closely related function. It's 0 when t is less than or equal to a, and 1 when t is bigger than a. F of t and g of t differ in value at t equals a, but no place else. So if we look at the Laplace transform of g of t, it is the integral from 0 to infinity of g of t e to the minus st, which is going to break up as 0 when t is less than or equal to a. Now g of t is 1 when t is greater than a. So we get the integral from a to infinity of e to the minus st dt. We've seen this integral before. It's what we got when we took the Laplace transform of ua of t, and we got e to the minus as over s, which is what we get here too. So the Laplace transform of g of t is the Laplace transform of f of t, even though the two functions differ at the point x equals a. So since both functions have the same transform, if we were to back transform, we could not hope that we would always get back to the original function, okay, because two different functions have the same Laplace transform. When you inverse transform, you can't get both of them. So we might get the wrong value at the jump when we back transform, but no place else. In most physical situations, this is really not a problem, as we will see, even with a discontinuous driving function. For an oscillator, the solution we get is continuous, so there are no ambiguities arising about a function value at a particular point. So let's look at some examples where we have oscillators and the driving force is a piecewise continuous function. So let's look at x double dot plus 4x equals g of t. X double dot plus 4x describes an undamped oscillator. G of t is going to be cosine of 2t when t is less than 2 pi, and it's going to be 0 when t is bigger than or equal to 2 pi. Notice that this is a discontinuous function because at 2 pi, the cosine of 4 pi is 1, and at 2 pi, this is 0. So there's a jump discontinuity at t equals 2 pi. Okay, so the way to write this in terms of step functions is to write it as 1 minus u 2 pi of t times cosine 2t. We see this works because when t is less than 2 pi, this term is 0, and you just cosine 2t. When t is bigger than or equal to 2 pi, u 2 pi of t turns on, 1 minus 1 is 0, so this whole mess is 0. So we multiply it out, and we get the following expression. Now transforming the cosine of 2t is easy. Transforming u 2 pi of t cosine 2t requires us to write cosine 2t as f of t minus 2 pi. And we know the way to do that is to take this function over here and to replace t by t plus a, where a here is 2 pi, so we're shoving in a t plus 2 pi every place we see a t, which because of the periodicity of cosine gives us the cosine of 2t. And this is the thing that we can treat as f of t minus 2 pi. So when we transform this we get e to the minus 2 pi s times the transform of cosine 2 pi, which is s over s squared plus 4. So that's the transform of that second piece. So when we do the entire problem, we're going to transform the left-hand side, which transforms the same way we're used to. Double dot transforms as minus x dot of 0 minus s x of 0 plus s squared cap x. 4x transforms as 4 cap x. This piece is the transform of the cosine of 2t, which is s over s squared plus 4. And now this piece is the piece we just talked about, which gives us s over s squared plus 4 times e to the minus 2 pi s. Now, when we collect terms on the left-hand side, we get s squared plus 4 times cap x, and this is what we had before. We divide through by s squared plus 4, and we get s over s squared plus 4 squared minus s over s squared plus 4 squared e to the minus 2 pi s. We remember that the Laplace transform of s over s squared plus b squared squared is t over 2b sine bt. So using our formula that the Laplace inverse Laplace transform of cap f of s e to the minus a s is u a of t f of t minus a, this becomes t over 4 sine 2t for this piece, and u2 pi of t, t minus 2 pi over 4 sine 2, t minus 2 pi for this piece. Okay, now if you look at this expression, what you discover is that when t is less than 2 pi, this term is 0, and you've just got t over 4 sine 2t when t is less than 2 pi. And when t is bigger than or equal to 2 pi, this is a 1. And you'll notice this t over 4 sine 2t cancels with this t over 4 sine 2t. Okay, and the reason it's sine 2t is because it's actually sine 2t minus 4 pi, but because of periodicity, that's the sine of 2t. So this t over 4 sine 2t cancels that t over 4 sine 2t. What we're left with now is this minus 2 pi over 4, which is minus pi over 2, times minus, which gives us a plus, sine 2t. So what we've picked up here is pi over 2 sine 2t when t is bigger than or equal to 2 pi. Now, if you check, you'll notice that when t is 2 pi, this term is 0. When t is 2 pi, this term is 0, which means these things match up and we have a continuous function, even though we had a discontinuous driving function. This time, let's drive an oscillator with a square wave. I can see this particular square wave has period 2 pi. Between 0 and pi, it's 1. Between pi and 2 pi, it's minus 1, and then it repeats that behavior forever. Now, the way to get this written in terms of step functions is the function is 1 between 0 and pi. At pi, you want to jump it down to minus 1, so you want to subtract 2, which we do with a minus 2 u pi of t. Now at 2 pi, we want to jump back up to 1. We add 2 times u 2 pi of t, which pops us back up. And now you can see what we do at 3 pi, down 2, then up 2, etc. And that gives us a square wave. Now that's going to be our driver. And what we're going to drive is the oscillator described by x double dot plus x. Now, this thing has characteristic equation r squared plus 1. That means the homogeneous solutions are going to be sine and cosine of t, a cosine t plus b sine t. And we should expect resonance because The period of our oscillator is 2 pi, and the period of our square wave is 2 pi. So they both have the same frequency. We should expect resonance. Okay, so now we're going to take this thing and we're going to Laplace transform it. Now the x double dot plus x transforms as minus x dot of 0 minus s x of 0 plus s squared cap x. For this thing, little x transforms as cap x, and we know how step functions transform. This thing is going to transform to 1 over s. This is going to transform to minus 2 s over e to the minus pi s, which is how the step function transforms. This one is 2 over s e to the minus 2 pi s, etc. Okay, so our initial conditions were set to 0, so these terms drop out, and we just got an s squared plus 1 cap x on this side, and this series of transforms of step functions on this side. Now we divide through by s squared plus 1, and we'll notice that a 1 over s factors out of this whole mess, and we're left with a 1 over s times s squared plus 1 times this expression. Okay, now what we need to do is a partial fraction decomposition for this 1 over s times s squared plus 1. We're going to write it as a over s plus bs plus c over s squared plus 1. Multiply through by the denominator, and we get 1 is a s squared plus 1 plus bs plus c times s. Now, there are some good values. S equals 0 kills off this term, and we just get 1 equals a. Okay, so we know that a is 1. Now, when you put in s equals I, this term dies off, and this becomes bi plus c times I, which is just going to give us minus b plus ci on this side. That has to equal 1. And we're thinking about 1 as 1 plus 0i, so the real part 1 is minus b. So b ends up being minus 1. And the imaginary part here is 0i, which is ci, so c is 0. We plug that information back into our partial fraction decomposition. A is 1, b is minus 1, c is 0. So we end up with 1 over s minus s over s squared plus 1. Now the inverse transform of that is 1 minus cosine t, and that's our little f of t. Now remember, when we transform back, we're going to be getting e to the minus as f of t minus a for each one of these little terms. Okay, so what's going to come back is f of t minus 2 f of t minus pi u pi of t. Okay. And f of t is just going to be 1 minus cosine t, as we've got up here. So we're going to get a 1 minus cosine t from this term. We're going to get a 2 times 1 minus cosine t minus pi u pi of t plus 2 times 1 minus cosine t minus 2 pi u 2 pi of t plus dot dot dot. And that's now what's written up here. And now we have to figure out what this thing is. Now, when t is less than pi, all of the u pi terms are 0, and we've just got this 1 minus cosine t. When t is between pi and 2 pi, this term turns on, and what we get is 1 minus cosine t minus 2, 1, okay, now cosine of t minus pi is minus the cosine of t because that's halfway around, and we pick up a 1 plus cosine t term here times this 2, and that's what we've got when pi is less than or equal to t is less than 2 pi. And now doing some simplifying, 1 minus 2 is minus 1, minus cosine t minus 2 cosine t is minus 3 cosine t. And that's the expression that we've got between pi and 2 pi. Now, at 2 pi, this term turns on. And what we're going to get is what we had before, just before it, which is the minus 1 minus 3 cosine t, now plus 2 times this expression. And the cosine of t minus 2 pi is exactly the same as the cosine of t. So we're picking up a 2, 1 minus cosine t. And now when you combine these things, you end up with minus 1 plus 2 is 1, minus 3 cos t, 2 cos t, 5 cos t. Now we just keep doing that, and what we end up seeing is that these terms that sit out in front, the constants, bounce between plus 1 and minus 1, and the coefficients of cosine go up by 2 each time, and they're all negative. And this is the general formula that we get. But what's important to notice here is two things. Number one, notice how these coefficients go up, and they essentially go up linearly. So our amplitude is getting bigger and bigger in a linear fashion as we head off, which is resonance. The other thing to notice here is at pi, the value of this thing is 1 minus minus 1 or 2. At pi, the value here is minus 1 plus 3 or 2, continuous. At 2 pi, this thing is minus 1 minus 3 or minus 4. At 2 pi, this thing is 1 minus 5 times 1 or minus 4, continuous. And as we go through here, all of these things match up. So our solution is continuous, and it is behaving like a resonant solution in that the amplitude is growing linearly with time.